this lecture, we are going to discuss how to write the Maxwell's equation in tensor form. So before discussing in detail how to write the Maxwell's equation in tensor form, first we will discuss about the procedure for symmetrization, anti-symmetrization. Suppose now let us consider an arbitrary tensor. We are considering arbitrary tensor which is A-I-K. So this is an arbitrary tensor. Now if you sum over all permutations of the indices, giving a plus sign to an even permutation and a minus sign to an odd permutation. So here you consider A-I-K-L. So the first term is A-I-K-L. And the second term you make one permutation. You are interchanging I to K. So this becomes Ki. So this is Ki and this is K. So now this is one permutation. So this is an odd permutation. So you get a negative sign, minus symbol. Then you make one more permutation. So IL, here this is Li. So the second permutation. So this is the symbol is positive. Then again you interchange I and K. So this I and K. So this is the third permutation. So you get a minus sign. And here a fourth permutation, L and I. So this is the fourth permutation. So this is symbol is plus. And this is the fifth permutation. So here this K and I. So this is again odd permutation. So you are having 6 terms, 1, 2, 3, 4, 5, 6 terms. Therefore here you are using a 1 by 3 factorial, 1 by 6. So if you have an A-I-K-L is an arbitrary tensor, and by this process you can get a symmetric tensor. So this symbol, this big symbol, this is a curly symbol. The curly symbol and the tensor is put within the curly symbol. So the whole thing we call as an anti-symmetric tensor. So if A-I-K-L is an arbitrary tensor, it can be anti-symmetrized by this procedure. So you call this is equation 1, P1. So this is how to anti-symmetrize an arbitrary tensor. Now next we discuss one theorem. For every tensor field, one has A-I-K-L semi-covariant. So this is the covariant derivative of the tensor I-K-L. So covariant derivative, that means what? Partial d A-I-K-L divided by dxl. So we are differentiating with respect to the coordinate xl. So this covariant derivative, and you put this vector, this tensor within the curly bracket. This is equal to A-I-K-L comma m. So this is a normal derivative. Here this is a covariant. So these are equal. So A-I-K-L comma m within the curly bracket, which is the same as A-I-K-L semicolon m within the bracket. So the covariant derivative of A-I-K-L with respect to m is the same as the normal derivative of A-I-K-L with respect to m. And this is a bracket represents the anti-symmetry. So if you first take the covariant derivative and anti-symmetrize, which is the same as take the normal derivative and anti-symmetrize. Both are equal. This is property P2. So because we are going to use this property in the further discussion. Now next one is, now let us consider anti-symmetric tensor Tik. This is an anti-symmetric tensor. Now you take Tik comma L. This is the normal derivative of this tensor, and you anti-symmetrize it. So now if you put Tik-L is a normal derivative, and you put this bracket, curly bracket means this tensor is their anti-symmetry. This is equal to 1 by 3 of Tik comma L. This is the normal derivative plus Tkl comma I. This is again the normal derivative with respect to coordinate xi. Tli comma k, which is the normal derivative of Tli with respect to coordinate xk. So this is a property P3. So this can be easily proved. This is can be easily proved because you consider the term TIKL, T plus TL comma K, TL comma I. So you consider this term. Now you interchange I to K. So yeah, I to K you are interchanging, I to K, I to K. You are interchanging on this expression. Now let us use this property. IK, you interchange I and K again. So I get, if you interchange, you will have a negative sign. So this once if you interchange, you have this is a minus of Tik comma L, and here interchange your I and L. So this becomes T minus T Li, and you interchange this one, you will get this one minus this. So by interchanging Ki and in the first term, IL in the second term, and Lk in the third term in this equation, you will get a minus of this expression, which is minus of this. So if you take this one minus this common term, you will get this. Now, so this term Tik comma L plus Tkl comma I plus Tli comma Ik is equal to minus of this expression. Now you substitute this back to here. This suppose if you consider Tik comma L, this is a tensor. You are differentiating this is the normal derivative, and you are anti-symmetrizing by the definition using P3 P1. Using P1, you are expressing this expression 1 by 3 factorial in the Tik comma L minus Tki comma L plus Tkl comma I minus Tlk comma I plus Tli comma K minus Til comma K. So using P1, you first you expand this one, and you take the first term, positive terms alone. This is the first term, third term, and fifth term. This is the positive term. All the negative terms put together, you will get this expression. Your Tikl plus Tkl comma I plus Tli comma K. So if you substitute back, you will get this is actually previously this 1 by 3 factorial, because here you have this term plus again you have the same term. So 2 times of this expression. So on simplifying, you will get this result. So this P3 can be easily verified by using the property of anti-symmetrization. Now we are going to use the P1, P2, P3 in our later discussions. Now let us first take the Lorentz gauge. The electric flux and the magnetic flux are given in terms of the scalar and vector potential. This is E. So this is the electric field vector, and this is the vector potential A. Phi is the scalar potential. So E is related by this expression, minus 1 by C partial dA by dt minus gradient of phi. We take this one expression. Another expression is B is related to the magnetic vector potential, curl A. So you consider take 1 and 2. So this is we call this Lorentz gauge. Now in our previous lecture, we have defined a contravariant vector operator by partial d superscript I is equal to partial d by dxi, which is given by the 4 vector formation. So first I put I is equal to 0, d by dx is 0, and the remaining 3 is minus del operator, minus of del operator. So this is the equation 3. So this definition of this operator was discussed in our previous lecture. Now here the first coordinate x0 is your CT, and x1 is your x coordinate, x2 is equal to y, and x3 is equal to z. So it is the 4 vectors in the Minkowski space. So this is the 4 vector in the Minkowski space. Now the x components of the equation 1 and 2 can be written using 3. So using this vector operator, the equation 1 and 2 can be expressed like this. So first let us write down the x component. Here Ex is the x component of equation 1, and partial dx by dt is the x component of equation 1, and this is gradient phi. The d partial d phi by dx is the x component of this one. This can be expressed in terms of the operator. So using equation 3, this is a partial d0 a1, d the superscript 0, that means partial dA1 by dx0, that is the mean, minus partial d1 a0. So here this is equation 4. So the x component of the electric field can be expressed like this, where d0 d1, this is a expression in terms of equation 3. Now similarly, the x component of equation 2, this is x component of b is equal to, you write down the x component of curl a. X component of curl a is partial dA z by dy minus partial dAy by dz. So this is the x component of dx. So in terms of the vector covariant vector operator, this is minus of the partial d superscript 2 a3 minus partial dA3 by a2. So this is equation 5. Now d0, d1, d2, d3 are can be expressed in terms of the equation 3 that we have already discussed here. And what is a0, a1, a2? So the ai is equal to a0 comma a1. a0 is equal to 5, and vector a, there are 3 components. So a1 is equal to ax, a2 is equal to ay, a3 is equal to a. So these are the x, y, z components. So this is 4 vectors. So first one is the scalar potential. This is components of vector potential. Now this form of Ex and Bx suggests that we define a second rank tensor. Now we are going to define this tensor Fij. This is a second rank because there are 2 index ij. So this is a second rank contravariant tensor. This is defined by minus diaj minus djei. So the negative sign outside. This is a bracket and this is minus can be taken outside. So equation 6 is the components of the second rank tensor can be defined using this one. So now from equation 4 and 5 we get an idea about the equation 6. So 6 can be, so we get an idea about the 6 from equation 4 and 5, and here this is equation 4 is the electric this is the electric field component, B is the magnetic field component Bx. This Fij is the this is a component of contravariant component of the tensors Fij. And now from this equation we see this is Fij is equal to minus Fij. This is a, you can easily check that this is an, and if you put if you can put I to j, j to I, you will get Fij is equal to minus Fj. So this is an antisymmetric tensor. If it is an antisymmetric tensor, the diagonal elements must vanish. So the diagonal elements of because since it is a rank 2, the components can be expressed in terms of a matrix, and the diagonal elements of this matrix will vanish. So when you put F1 0 0, F1 1, F2 2, F3 3, they all will vanish. So the diagonal elements will vanish for distance. Now in equation 6, if we choose j is equal to 0, and if you put I is equal to 1, 2, 3, then we see that from equation 4, F10 is equal. So you get F10. So from the definition that we have discussed from equation 6, this is partial d1 a0 minus and 0 A1, and this is equal to minus Ex. So F10 is equal to this minus, and so you can easily check this one, because if you put F20, if you put I is equal to 2j is equal to, so this is 0, this can be easily obtained. This is minus ui and this is a minus u. So so from equation 6 we can get this idea. From equation 6 you can get this one, this expression, and you will get minus Ex. F10 is equal to minus Ex, F20 is minus ui, F3 is equal to minus Ex. We may also find F12. If F12 is, according to the definition of 6, this is equal to this value, which is equal to plus Bz, and this is equal to F23 is minus Bx, and F31 is equal to plus B. So this can be easily found by using this expression. Now, so the tensor Fij. So how do you find Fij? Because this is I runs from 0 to 3, so 4, J runs from 0 to 4. So these components can be expressed in terms of the 4 by 4 matrix, and we have already calculated the F0, 0, F11, F22, F33. They all are 0 because this is an antisymmetric matrix that we have already calculated. And the components F10, F20, F30, and all the components are calculated just before. So you substitute all the components and you form the matrix, and this matrix Fij, this is a contravariant tensor of rank 2, and this tensor is having a name. This is electromagnetic field strength tensor. So this is a electromagnetic field strength tensor. So this equation 8 is important in deriving the Maxwell equation tensor. So this contains electric field components and magnetic field components. So equation 8 contains electric field components and magnetic field components, and therefore this is called the electromagnetic field strength tensor. Now let us write down the Maxwell's equation using this problem. Now there are 4 Maxwell's equations. Now all the 4 equations can be paired into 2. So the first pair contains curl H minus 1 by C E dot is equal to 1 by C J0. So this is one of the equations, and curl E is equal to rho is another equation. Now equation 1, this J dot is equal to partial dJ by dt, and E dot is equal to partial dE by dt, and equation 2, this is del E is equal to rho, and the del operator is I times partial d by dx plus j unit vector j times d by dy plus unit vector k times d by ds. Now here the j is called as the current density. Current density is the source of the electric field, and rho is the charge density. Charge density is the source for the magnetic field. Therefore, the equation 1 and 2 is called as the source equation. So the first pair usually we call this the source equation. Equation 1 and 2. So this is a source equation. Because this is a J is the current which is the source for the electric field, and the charge density is the source for the magnetic field. So this 1 and 2 is called the source equation. The another 2 equations we call this the second pair. Curl E plus 1 by C H dot is equal to 0. So this is equation 3, and divergence of H is equal to 0, which is 4. And these 3 and 4 are called as the internal equations, because the electric field and the magnetic field will be seen to be the complements of an electromagnetic field tensor. So this is called a internal equation, because here electric field and this is the magnetic field. Here magnetic field. So they are the components of the electric and the magnetic field vector fields, which will be the components of an electromagnetic field tensor. So E and H are the components of the electromagnetic field tensor. So this is an internal equation, because there is a relation connecting E and H. Now take equation 1 and take its divergence. So take the divergence of the first equation. First term is a divergence of 12H. Second term is divergence of E, 1 minus 1 by C divergence of E is equal to the right hand side, this is 1 by C into divergence of J. So you call this equation 5. Now similarly, if we take the second equation, and if we take the second equation is divergence of E dot, so you are differentiating equation with respect to time. So differentiating to with respect to time, the divergence of E dot is equal to rho dot. So divergence, actually this is with respect to time. So this is equation 6. So we are having two equations 5 and 6. In equation 5, this is a divergence of curl. Div curl is 0. Div curl is 0. So the first term is 0. The second term is divergence of E dot. So from 6 you can substitute. So this becomes 1 by C rho dot. So from 6 you can substitute. So this is a rho dot. This is the term in the right hand side. If we take the two terms in the same side, this is rho dot plus div J is equal to 0. So this is the relation, differential relation connecting charge density and the current density. So equation 6 is the relation connecting charge density and current density. Now if you interpret J, this is the current density, which is equal to J is equal to rho times V. V is the velocity of the field. So rho into V, we can define as the current density, because the rate of flow of charge per volume. So this is charge per unit volume. So charge into V will be the current per unit volume. So this is the current density. So J is equal to rho V. Now you substitute here rho dot plus div G and div J, and J is equal to rho V from your this definition. This is divergence of rho V is equal to 0. Now this is called as the equation 10 is called as the principle of conservation of energy. So this is rho dot plus divergence of rho V. This is equal to 0. This is the principle of conservation of charge, because this is a charge density, here is a charge, rho dot, here rho. So this is the principle of conservation of charge. So a source vector is already, so this is also we have already defined. We defined a source vector. S alpha runs from 0 to 3. S0 is rho, S1 is the component, and the x component of the current density Jx by C. This is Jy by C, and J is a rho comma J vector J by C. This is a 4 vector. So this is called as the source vector, source 4 vector. So equation 11. So this is already we have discussed in our previous lecture. So you choose this same symbol here. S alpha is equal to within the bracket. The first term is the S0, and the J vector by C. There are three components: Jx by C, Jy by C, and Jz by C. Now we are going to adopt a convention. If you use a Greek letter mu, it runs from 0 to 3. If you use a Latin J, it runs from 1. Just for convenience, we are using this convention. So according to the convention, the first term is C, because this is a rho dot. Rho dot is d by dx0. X0 is Ct. So you can write the first term is C times rho comma 0 plus the second term is ji comma I. So in terms of the source vector, so we already defined the source vector, you can write this expression. So equation 8, the conservation of charge, actually you just see. So this is your equation 8. So you refer the equation 8, and this equation 8 is equation 8 can be written in this form by using the definition of the source vector. So by using the definition of 11, you can write down equation 8 in this form: C rho comma 0 plus j I comma I runs from 1 to 3. So j1 comma 1, that means partial d j1 by dx1. j1 is equal to jx by 1 means partial dx. So you can, if you perform the summation I is equal to 1, 2, 3, you will get the second term of equation 8, and this is the first term. Therefore this can be simply written like this: S alpha comma alpha is equal to, this is a superscript and this is a comma alpha, this is a normal derivative. So if you put S alpha is equal to 0, what is the first term? S0 is what? S0 is rho, also d rho by, this is partial d of ct. So you will get this first term. So if you put S1 1, you will get the second term, and if you put 2, 2, you will get the second term. If you put 3, 3, you will get the third term. So equation 12 can be conveniently expressed in terms of equation 3 by using the source vector S. Now this is an ordinary derivative, normal derivative, S alpha comma alpha is equal to 0. Now this can be expressed in terms of the, this is important, the covariant derivative. We are using a semicolon symbol here. S alpha semicolon alpha is equal to 0. Because once if you take this derivative according to the definition, if you expand the equation 14, the first term is the normal derivative, and you have the second term which consists of the Christoffel symbols. But the Christoffel symbols are the derivative of the metric tensor. The derivative of the metric tensor. But here this G all, so once if you define the metric tensor to our problem, you will have only a diagonal elements. All the off diagonal elements are 0. Therefore Gij is equal to 0 for I is equal to 0. Therefore the Christoffel symbols are 0 in our this system, in this coordinate system. Therefore writing S alpha semicolon alpha is 0, this is the covariant derivative, which is the same as the normal derivative, because the first term will be the normal derivative, the other terms will be expression of the Christoffel symbols, but the Christoffel symbols are 0 in this coordinate system. Therefore this S alpha comma alpha can be expressed in terms of S alpha semicolon alpha, because once if this is a S alpha comma alpha is not a tensor equation, whereas because this is normal derivative, and S alpha semicolon alpha is a tensor equation, because it is the covariant derivative. So covariant derivative of a tensor is a tensor, a normal derivative is not a tensor. So now you are writing this in the tensor. So what is the advantage of writing the tensor equation? If tensor equation is satisfying all coordinate systems, that is important. Tensor equations are satisfied in all coordinate systems. Or normal derivative is satisfied only for the rectangular coordinate system. So here, whether the coordinate is a polar coordinate or rectangular coordinate or any curvilinear coordinate, equation 14 is satisfied. So since this is the most general way of expressing, because this equation S alpha semicolon alpha is equal to 0, which is the tensor equation, this is more advantageous when compared with the equation 13, because 13 equation 13 satisfies only for a rectangular coordinate system, whereas S alpha semicolon alpha 0 is satisfied for all coordinate system, whether it is a rectangular, polar or curvilinear coordinate system. That's why the tensor equation is much more advantageous. Now let us write down the source equation, because we are interested in writing the Maxwell's equation tensor form. So first we have the two equations, equation 1 and 2, they are the source equations. Among the four equations that you are considering, you combine the 1 and 2 in the source equation, and we have already defined the electromagnetic field tensor. This is we have already defined 0 Ex Ey Ez minus Ex, because since it is an anticipating tensor, the diagonal elements are 0, and this is the minus Ex minus Ey minus Ez, because since it is a positive here, this must be a negative minus of this one, because the antisymmetric tensor. Here Hz minus Hz, minus Hy here, and this is plus Hy here, and Hz here, and minus. So this is how to get this expression that we already discussed. So the electromagnetic field tensor can be arrived. That was discussed earlier. So from the result, you take this electromagnetic field tensor F mu nu, which is equation 15. Now using this matrix, we write the source equation. So F mu nu comma nu is equal to S nu. So the equation 1 and 2 can be expressed in this way. This is normal derivative of F mu nu, which is in S nu. This represents the equation 1 and 2. If this is satisfied in the rectangular coordinate system, since the Kirchhoff symbols is 0 in the rectangular coordinate system, or in this space is a 4-dimensional space, or relativistic space in a specific space. We are dealing with a special theory of relativity, which is a Minkowski space. In that space, the Kirchhoff symbols are 0. Therefore, you can express F mu nu semicolon nu is equal to S nu. So instead of writing the normal derivative, you can write down the covariant derivative. So once if you write down in terms of the covariant derivative, this equation is a tensor equation. So now let us verify this equation 16. So let us verify that the equation 60 is equal to the Maxwell's equation 1 and 2. So we have to. So first you consider this equation F mu nu comma mu is equal to mu. First consider this one. You put mu is equal to 0. So this is F 0 and mu comma nu, which is equal to, you put mu is equal to 0. This will be 0. So this is the first step. Then there is a summation over nu. Now let us perform the summation. Nu runs from 0 to 3. So if you perform the summation over nu, the first term is F 0 0 comma 0. Second term is F 0 comma 1. The third term is F 0 2 comma 2, and the fourth term is F 0 3 comma 3, which is equal to S. What is the meaning of this one? F 0 0 comma 0, partial df 0 0 by dx is 0. So that is the meaning of the first term. Partial df 0 1 by dx1, this is the second term, and this derivative partial df 0 2 by dx2 is the third term. Partial df 0 3 by dx3 is the fourth term, which is equal to S0. Now what is x0? X0 is ct, and here x1 is equal to x, and x2 is equal to y coordinate y, and this is z coordinate. Now what is f00? F00 is 0, because from the we have already given the electromagnetic field tensor, so you know the F mu nu. So from F mu nu, you know F00. So from the matrix we see that the F0 is 0, therefore the first term is 0, and the F01 is equal to Ex. So we substitute here Ex. F02 is Ey. F03 is Ez. So from the matrix F mu nu, you just substitute the values of F00, F01, F02, F03. You will get this expression. and this is partial dEx by dx plus partial dEy by dy plus partial dz by dz is equal to, and what is S0? The 4 vector. The first vector is row vector. So this is a row. Now this equation is just a divergence of u. Divergence of u. Once if you substitute for this del operator, you will get this expression. So you combine all the three terms, and this is equal to divergence of u. So if you expand, you will get partial dx by dx plus partial dy by dy plus partial dz by dz. So the left hand side of this equation, where the expression is divergence of u, on the right hand side this is rho. So this is the 90, equation 90. So now this is the Maxwell's equation 1. So this is your Maxwell's equation 1 that you discussed here. Now for mu is equal to 1. For mu is equal to actually this is a we will discuss this is Maxwell's equation 2. This is Maxwell's equation 2. Now if you put for mu is equal to 1, in that expression 16, this is f. You put mu is equal to 1. This is mu is equal to 1 in that equation 1. 16. So this is f is equal to f mu 1. This is mu, and there is some mu. So which is equal to S1. Now what is you have to perform the summation over all mu. So first term mu runs from 0 to 3. So first term is f10 comma 0, and the second term is f11 comma 1. Third term is f12 comma 2, and the fourth term is f13 comma 3, which is equal to S1. So if you perform the summation over mu, you will get this answer. Now this may be expressed like this: partial d of f10 comma 0 means df0 by dx0. x0 is ct, and here the second term is, and this is x1, partial dx1, which is a coordinate x1, here coordinate x2, here coordinate x3, which is equal to x1. From the matrix you know the electromagnetic field, from the electromagnetic field tensor, the components of the electromagnetic field tensor, you just take the value of f10. f10 is equal to minus ex, and this divided by partial dct, and the second term f11, since it is a matrix, symmetric matrix, f11 is 0, so this is 0, and the f12 component is from the, you look at the field tensor, and the components f12 is hz, and x2 is y, so partial dhz by dy, and the last component is minus partial dhy by dz, which is equal to S1. What is S1? From the 4 vector, definition of the 4 vector, S0 is rho, S1 is dx by c, so this is dx by c. Now this will be, you take a minus sign outside and c outside, and partial dx by dt is x dot, plus you combine these two terms. The two terms are x component, this is a curl h comma x, the x component of curl h. So the third and fourth term, if you combine, this is the x component of curl h. On the right hand side, this is 1 by c jx, or you can write this is curl h comma within the bracket, and the suffix is x minus 1 by c e dot suffix x is equal to 1 by c j suffix. This is called as the x component of Maxwell's equation. So we have arrived the x component of Maxwell's equation 1. Then similarly, you can if you substitute the other values, you can get the y component of the matrix, the Maxwell's equation 1, and also the z component of the Maxwell's equation 3. So if you substitute the other values of mu and nu, you will get the x and y components of the Maxwell's equation 1. So combining all the three, we get the equation 4. So this equation curl h. So if we combine x component, y component, z component, we get this expression. Curl h is minus 1 by c e dot is equal to j eta j by c. So this is actually Maxwell's equation. This is same as equation 1. So Maxwell's equation 1 and 2 that we have obtained. So we have obtained three equations. So one is equation of continuity in tensor form, and the equation Maxwell's equation 1 and 2, which is the source equation that can be also expressed in tensor form. Now, next we consider a notation. So you consider this term f mu nu comma lambda. This is a covariant vector f mu nu comma lambda plus f mu lambda comma mu plus f lambda mu comma nu. This is equal to 0. So you consider this expression. Now, if you antisymmetrize, this can be expressed by mu f, because f mu nu is already a symmetric tensor. F mu nu is a symmetric tensor. If it is a symmetric tensor, then we can write f mu nu comma lambda within the bracket, within this curved bracket. This is can be expressed as a antisymmetric tensor. So you are antisymmetric. So this equation 23 can be written like this, whereas this is an antisymmetric tensor, because we have already discussed in property 2, P2 and P3. We know that this f mu nu comma lambda, and if you antisymmetrize, so this expression can be expressed in this way. So equation 23 can be written in the form of 24 according to the property P2 and P3. Now let us verify. Now to verify this one, because this is a covariant tensor f mu nu, but the contravariant field tensor, these components of the contravariant field tensor we have already derived. So we have obtained this value. So if you know f mu nu, the contravariant metric tensor, then the covariant components can be obtained by this process. So f mu nu is equal to g sigma mu, g lambda nu f sigma lambda. So the contravariant, so the lowering of indices. The lowering of indices can be done by multiplying, by making a product with a covariant metric tensor. To multiply a covariant metric tensor, one index will be lower, and if you make another inner product, you will the two index may be lower. So the contravariant metric tensor can be from the components of the contravariant metric tensor. You can get the components of the covariant metric tensor by this process. Now here this is g mu nu, g lambda mu. This is a covariant metric tensor. Now what is g mu nu? This is we already know, because this 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus, because in our Minkowski space, and the diagonal elements are 1 minus 1 minus 1 minus 1, all the off diagonal elements are 0. Now let us find the covariant components f 0 0. So you put mu is equal to 0 and mu is equal to 0. So if you put mu is equal to 0, and this is g sigma 0 and lambda 0 and f sigma. So this is the first step. You put 0 0. Then you perform the summation over nu and lambda. So if you perform the summation over sigma, the first term is 0, here 0, 0 0, alright. Here f 0 lambda. Then for this, again you have to perform the summation over lambda. So if you perform the summation over lambda, because if you put sigma is equal to this is 1 0, the next term 1 0, if you put this is 1 0, this is g lambda 0, alright, then you perform the summation f 1 lambda and so on. So you perform, so if you make a sum over all sigmas and all lambdas, you will get many terms, and the terms except this term, all the other terms are 0, because lambda 1 0 is 0, lambda 2 0 is 0, and so on. So all the off-diagonal elements are the components of the off-diagonal elements of the matrix G are G mu are 0. Therefore, all the other terms are 0. So we have only having this term, and even this term. Now let us expand this term. You perform the summation over lambda. So the first term is 0 0, and here we put lambda is equal to 0. This is G 0 0, F 0 0, and the second time is, and this is 0 0, and we put lambda is equal to 1 0, and because lambda is equal to G 1 0 is 0, all the other terms are 0. So if you want to calculate F 0 0 using the expression, you have to perform the summation, and once if you perform the summation here, that expression, summation over mu and lambda, only a term with 0 0 and 1 1, G 2 2, G 3 3 alone will be present. All the terms with the Ij are different as 0. Therefore, so you have only this term. So this is 0 G 0 0 and G 0 0, F 0 0. Now even here, what is G 0 0? G 0 0 is 1. Therefore you put 1. Again this is 1. But what is F 0 0? F 0 0 is 0. Therefore, so the covariant component F 0 0 is same as, which is equal to 0. So the first one component we have determined. So what is F alpha alpha 0? This is the both are same indices. Whether it is F 0 0, F 1 1, F 2 2, F 3 3, all the values are 0 because it is an antisymmetric matrix. So all will be 0. Now let us calculate F 0 1. Here put first the non-vanishing value. So you put this is 0, this is mu 0, mu 1, and summation over sigma and summation over lambda, and the only non-vanishing values are, this must be 0, same, both are identical, C 0 0, and this must be also only identical because the diagonal elements alone will be present. For all the other elements will be 0. So I am not writing all the other elements. Just for explanation I am given the in the previous expression all the elements, all the terms. Now in order to calculate F 0 0, let us write down the non-vanishing elements alone. So G 0 0 is plus 1, G 1 1 is minus 1, and F 0 1. F 0 1 from the matrix you can easily see this Ex. So this once we multiply with minus x. So F 0 1 is this value. Similarly, you can calculate F 0 t is minus Ey, F 0 t is minus Ex. Similarly, let us calculate a component F 1 0. F 1 0 is, you put mu is equal to 1, mu is equal to 0, perform the summation over mu, perform the summation over lambda. Only when the two indices are equal, you have non-vanishing value. Only the two these indices lambda 0 are equal, you have the non-vanishing value. Therefore, the non-vanishing values are, this must be G 1 1, G 0 0, and this must be F 0 0. All the other terms are 0. So there are all the other terms which gives 0, we are not writing. So we need not write. So only the non-vanishing terms alone can be written. So G 1 1, G 0 0, F 1 0, G 1 1, this is minus 1, G 0 is plus 1, and F 1 0 from the matrix you can say this minus Gx. So you can find this value is plus Gx. So F 2 0 is y, Ey, F30 is easy. So these terms can be also calculated by using this property. Similarly, F12, mu is equal to 1 and mu is equal to 1, mu is equal to 2, and so you perform the summation over sigma and perform the summation over lambda. The only non-vanishing terms are G11, G22, F12. G11 is minus 1, G2 is minus 1, F12 from your contravariant component F12 is Hz. So substitute you will get. So like that this F13 can be calculated. F23, the non-vanishing term can be also determined. So this is we found this is Hx, F31 is Hy, F32 is Hx. So the contravariant F minimum, the components of the contravariant tensor, you can write down the covariant components of the field tensor, that can be determined. So this expression, so if you put all the results in the matrix form, you will get this equation 25. So from the contravariant, one, you can get the covariant components by this process. So once if you know the covariant component, then we can easily verify equation 14. Now you put mu is equal to 0, mu is equal to 1, lambda is equal to 3, then the term, that is the antisymmetric vector, that term is F01, 3, F13, 0, plus F30, 1 is equal to 0. So that actually this is equation. What is this equation? Equation 23. So in equation 23, you will get this expression, and this can be expressed by partial d f0 by partial dx3, partial df13 by dx0, partial df30 by partial dx1, and you know x1 is equal to x, and x0 is equal to ct, and x3 is equal to dz, and here f01, f13, f31, that is can be obtained from your previous equation. So 25. So using equation 20, the matrix here 25, you can get this expression, and you combine these two, you will get this is the y component of curl E, and the rest of the vector is 1 by c d h by dt. So this is the y component. If you put mu is equal to 0, mu is equal to 1, lambda is equal to 3, you will get the z component of this vector. And if you put mu is equal to 0, mu is equal to 2, lambda is equal to 3, then you will get the x component. So the x component, y component, z component can be determined. So you combine equation 25, 26, 27 and 26b, 26a, 26b, 26c, you will get this curl E. This is a curl E plus 1 by c h dot is equal to 0, which is your equation 3 of the Maxwell's equation 3. Similarly, if you put mu is equal to 1, mu is equal to 2, lambda is equal to 3, and the symmetric equation is so actually from equation in equation 23, you will get this expression. Now you as before we have this can be expressed in terms of partial d of 12 by partial dx3 plus partial d of 23 by partial dx1, and this is partial d of 3 by partial dx2, and if you substitute the components f and the covariant components f12, f23, f31, you will get this expression. And this is from this is the divergence of x. So divergence of x is 0. Similarly, for mu is equal to 2, mu is equal to 3, lambda is equal to 1, again you will get this divergence of x. So this is equation 4. So this is equation 4. This is a Maxwell's equation 4. This is a Maxwell's equation. So 3 and 4 can be obtained by using this expression. Therefore, this bracket, curved bracket of f mu comma lambda is equal to 0 is the tensor equation of the Maxwell's equation 3. So this is one of the Maxwell's equation. So this is a Maxwell's equation. Actually this equation 3 and 4 is one of the Maxwell's equation. Again this is a tensor equation, because once if you put a curved bracket, this is a tensor equation, and it is a tensor equation, and this will be satisfied for all coordinate, whether it is a rectangular or polar or curvilinear, and this will be satisfied. And the same equation can be put in the other form also. Here this is a star f minimum. This is called as a dual tensor. This is a dual tensor. Semicolon nu is equal to 0. So the same thing can be expressed in the other form. So this is called as a dual matrix, star f minimum. This dual matrix is defined by star f minimum is equal to half into E mu lambda sigma f lambda sigma. So the dual matrix is expressed in this form. Now here the meaning of E mu lambda is this is equal to 0 if two indices are equal. If there is plus 1, if they are mu lambda sigma are even permutations. If this mu lambda sigma are odd permutations, it is minus. So that is the meaning of E. Now from this star f00, star f41, star f22 and star f23 will be 0. So this is again you can easily show that this is an antisymmetric matrix, because once if you put 0 0, two indices are becomes 0. If you have 1 1, two indices are 0. 2 2, two indices are 0. So the two indices are 0. All these 4 point indices are 0. All right. Then star f01. So this is the 1th component of the dual matrix F. This is expressed by using the definition. The definition is equation 19. By using equation 19, so here using equation 19, equation 29. Equation 29, you can write this one. So your star f01 is equal to half E01 23 f23 plus half E01 23 f2. So we are writing only the non-vanishing terms alone. All the other terms will be 0. When the two indices are repeated, it will be 0. So the only we are writing non-vanishing terms. And here this will be plus 1, and here this is odd permutation, this is minus 1, and E f23 f32. This from the matrix that you have already defined, you can take the components of 2 3 and 3 2. This is f23 is x and f32 is minus x. So once you substitute these values, so star f01 we have calculated. Similarly, star f02 is again this is of 02. The other only non-vanishing values will be present only if this must be a different indices than 0 or 2. Other than 0 or 2 you can try. So 1 2 here, 1 3 here, so here 3 1. So here 1 3, here 3 1. For all the other indices it will be 0. So now this is 0 to 1 3, this odd permutation will have a minus value, and f13 from the matrix the components are minus xy, and this is E02 31 is the even permutation, so this is plus 1, and f31 from the components of the field tensor, it is xy. So substitute all these values will similarly star f3, that can be also determined, which is equal to h is so you substitute all the, so similarly all the other components are found on the matrix star f meaning, that can be star f meaning. So this is the covariant component of the dual tensor. So you write down all the components that you have determined in the form, and this is equation 30. So equation 30 gives the components of the covariant components of the dual tensor. Now let us calculate the contravariant components. So the contravariant components, now let us evaluate all the components. Here also, when this is 0 for mu and mu is equal to 0, both are identical. It is 0 0 or 1 1 or 2 2 or 3 3, all these components are 0. So now let us calculate the non-vanishing terms and the contravariant components of the field and dual field tensor. So this is a dual tensor. So 0 G 0 0, because this is a contravariant component that can be obtained from the covariant component. So this is a raising of indices. So during raising of indices, we are using the covariant contravariant metric tensor. Once if you multiply with the one contravariant metric tensor, one index is raised, and if you multiply two contravariant metric tensor, two indices are raised. So the two indices can be raised by using this process. Now you perform the summation over all the indices. So here the non-vanishing terms allowed are present only when, so this is a G 0 0 G 1 beta star F 0 beta. Here also, when if you put alpha is equal to 0, if you put alpha is equal to 0, G 0 0, so the alpha is different from 0, because only the diagonal elements alone is present, because the contravariant metric tensor, the diagonal elements are the inverse of the diagonal elements of the covariant metric tensor for all the other elements are 0. So using this property, G0 alpha is equal to 0 for alpha is not equal to 0. Therefore, the non-vanishing terms are G00, G11 star F01. And here G1 beta is equal to 0 for beta is different from 1. Because if you put 1 1, you will have a non-vanishing value. If it is different from 1, this will be 0. So you are writing only the non-vanishing terms. All the other terms are 0, because all G I alpha beta, they are different. Alpha is different from beta, they are 0. Now G00 from your matrix, this is 1, G11 is minus 1, that is the all. Yes. So this is G00 is 1, G11 is minus 1, and star F01 from the matrix that you have already calculated, you substitute this value to the minus x. So the component star F02, the contravariant component, and this is the dual matrix. For the dual matrix, the contravariant component is obtained in this form. So this is in order to get the non-vanishing term, you put this must be same indices. This must be a same indices 2 2, and this is that you can substitute from the your matrix. So this is Hy, and this value is G00 is 1, G22 is minus 1. So finally you get minus Hy. So similarly, this component star F03 can be also determined. So all the other components can be determined, and the contravariant tensor star F mu can be evaluated, which is 0, minus Hx, minus Hy, minus Hz. Here this is the Hx, Hy plus Hx, plus Hy plus Hz in the row. Here this is the diagonal elements are 0 because the non-symmetric matrix, anti-symmetric matrix, and this is Ex and this is minus Ey. This component is minus Ex and this is plus Ex. If it is plus Ex, this must be minus Ex. And this. So these components can be evaluated and substituted with the equation 32. Now you compare the two expressions. One is F mu that you already determined, and here this is the dual matrix. And if you just compare, you will find that the components of E in your F mean matrix are changed into minus X, and the components of H in the F mean matrix are changed into. So just you know that you compare the two matrices, you will find that the E components in F mean are changed into minus X, and H components are changed into E components in the dual matrix. Therefore, the differential expression, so this is your expression already, F I nu comma nu, which is equal to curl H minus 1 by C eta. This is the differential expression that we are given. This goes into Fi, this goes into star dual matrix. This goes into star. So once if it goes into star, then this expression H goes to what? H goes to E. So this goes to E, and E goes to minus H. Therefore we get this. So this expression goes to this expression, and if this is a electromagnetic tensor, this is a dual tensor. So once if you convert this into dual tensor, then the Maxwell's equation will be like this: curl E plus 1 by C H dot. So this is equation 33. So the Maxwell's equation 3 and 4 becomes like this. So you can write down Maxwell's equation 3 and 4. So this is a so the if you combine all the results, this is one equation, then Maxwell's equation in tensor form. This is one equation. This is equation 1 and 2, and the 3 and 4 is either this form. So this is a tensor equation, or it can be expressed in this form also. This is also a tensor form, but this is a matter. This is a dual tensor, and this is the equation of continuity. So equation 35 is Maxwell's equation 1 and 2. This represents equation 3 and 4. 3 and 4. This is a equation of continuity. Equation 35, 36, 37 are the tensor equations, which are 35 is the Maxwell that represents Maxwell equation 1 and 2, which is a tensor equation, and 36 there are two forms. Either this can be expressed in the antisymmetric form F mu nu comma lambda is equal to 0, or a star F mu nu semicolon nu is equal to 0. Both are tensor equations. 36. This represents Maxwell's equation 3 and 4. And equation 37 represents the equation of continuity. All the tensor equations. So these tensor equations are much more elegant form. It's a very simple, elegant form. Also, this tensor equation will be satisfied in the not only in rectangular coordinate system, but also in the other coordinate system.